Welcome, everyone. My name is Eric Shanks. I'm a principal technical marketing engineer from Portworx by Pure Storage, and I'm super excited to talk to you today. I don't get to talk to platform engineers as much as I would like, and this is a great opportunity for us to chat. Before we get into some hands-on labs that we're going to go through here in a little bit, I got to get something off my chest. So if you guys don't mind, real quick, hey, Humanitech, meet me at camera 2. You know what you did. You took the easy way out. It's okay. We do this from time to time, but come on, Humanitech. I know what you're doing here, and I'm not okay with it. We're going to discuss this further. So for those of you who don't know who I'm talking about here, let's look at some of the reference architectures that Humanitech has put out, right? They're trying to help us understand all of the pieces that need to go together for a typical platform. So if I look at several of their reference architectures that they published online, here's one for an internal development platform on AWS. And the thing specifically I'm looking at here is in the resource plane, I've got highlighted a section here for data. And for the data section, we've just chosen a typical managed database service like RDS for MySQL for this example, right? Managed databases are kind of one of those things that we know we're going to need some sort of persistent data for our applications, a backing service for our 12-factor application, and we've got a managed service from the cloud provider, which seems like the easy solution to us, right? So for AWS, they chose RDS. If I look at GCP, they did something similar. They used a managed service for Google Cloud SQL here. And if I look at Azure, of course, they've got Azure SQL here as their example for the data layer. What I'm going to suggest, though, is that these managed databases aren't necessarily the easy option. Let me take a step back here and explain. So I was a consultant for about 10 years. I focused on data center infrastructure. I focused on cloud deployments. I focused on a little bit of DevOps here and there. I focused on Kubernetes. But one of the main things that I did while I was a consultant was focusing on getting applications from being built into a production environment. A lot of the times back when I was doing this, we were just deploying virtual machines. So I was using tools like cloud management platforms like vRealize Automation or Cisco UCS Director. It's kind of the olden days. It wasn't even called platform engineering at the time, right? This was more about cloud management. But what we were trying to do was some similar things. And as platform engineers, you probably already understand the idea here that one of the main challenges of platform engineering is limiting complexity. So complexity is kind of the enemy of velocity. We're trying to get our applications deployed quickly and, more important, reliably, and we have to manage all these applications over time. Now, we have this funny balancing act that we have to do as platform engineers, right? We're trying to give our application developers or the teams that are developing our applications enough options so that they have very flexible capabilities to do their deployments. They can use whatever tools they want to, and we're trying to provide those infrastructure tools to them based on what they're looking for. But the number of options that we give to those developers increases the total number of outcomes that we as platform engineers have to manage, right? For example, if I let developers choose which cloud they might be deploying to, right? They could deploy to Azure or Google or AWS. But then we might give them another option on top of that. In this case, say a managed database. Well, if I'm deploying to AWS, I can use I can use RDS. If I'm using Azure, I can use Cloud SQL, for example, right? And then we might have additional options on top of that, like logging. Well, how do we do logs in AWS versus Azure? And so every one of these options that we give increases the total number of outcomes that we have to manage, right? So that's increasing our complexity as platform engineers. And we need to have this balancing act, right? We want to limit the number of options so that we can manage those, but we also want to have enough options so we're giving those to our development teams, right? So with all of these outcomes, if we're developing too many features that we can't really manage them, we're increasing the complexity for things like multi-cloud environments. We have fragmented management and monitoring, right? Each environment might have a different tool, or each form factor for like virtual machines or Kubernetes containers might have different management and monitoring tools that they have to use, and we have to integrate those. We might have security and compliance gaps depending on how we're doing our deployments, we might have to use one or different compliance rules to make sure that those things work for us. Reliability changes depending on the form factor of our deployments, a VM, a container, or a managed service. We have to do different things to make sure that they're highly reliable and we know they'll work all the time. And of course, each one of these options we provide includes its own set of dependencies that we have to manage, right? So what I'm trying to suggest here is limiting the number of outcomes can make us faster as platform engineers. Another thing I like to talk about, and I don't get to talk about this enough with the infrastructure teams that I work with most often, but is the concept of Brooks's Law. Hopefully some of you in this group know who Brooks's Law, what Brooks's Law is about. But if you're not familiar with it, it's coined by Fred Brooks. And basically what it says, if I've got a project that's running behind and I add more people to that project, I'll make it later. So it's kind of counterintuitive to the way we typically see management look at projects, right? A lot of times it's like, oh, this is running late, let's throw more people at it so we can get it out faster. And kind of what happens is the opposite. And the reason for this is the number of communication channels that we have to manage. So as you can see from the diagrams here, if I had 4 people on a team, that's 6 communication channels. Everybody has to talk to each other. We all have to know what we're doing so that we're not building code and things in opposite directions, right? We need to be tied together. We need to work as a team. If I add one person to that group, I go from 4 to 5 people, but I go from 6 to 10 connections, right? So I'm increasing the number of the complexity really about how my team is structured. And of course, if I go up to 6 people, now I have 15 connections. So the more people I add to these teams, the worse this problem kind of gets, where I have to be constantly communicating with people, right? This is one of those reasons where you hear terms like a 2-pizza team that Amazon coined, right? Where they never want a team that's bigger than a size that the team can eat 2 pizzas, right? If I need a 3rd pizza, our team's too big. So that's kind of what we're talking about in terms of complexity here with the number of people. So let's put this in context. So kind of been thinking about some things in a theoretical fashion here. The technical marketing team at Portworx uses 3 completely made up demo applications, all formed around the idea of this fictional company that's a barbecue restaurant, right? So in this case, let's put our shoes in, our feet in the shoes of a platform engineer at this Portworx barbecue fictional company. So for this, we're going to use 3 different applications. 2 of these applications you'll actually see in your labs later today. The first application is Portworx Barbecue. It's our front-end restaurant application. It's where people can go online and order their own barbecue ahead of time, and they can see our menu and all those types of things you're used to a typical restaurant having, right? And its backend database is a MongoDB database. The second application is called Barbecue Bookkeeper. And it's a way for our fictional barbecue company to manage inventory across all of the restaurants across the US. And it uses Microsoft SQL. We can assume that it's managed by a different development team, and they've made a different choice for their backend data service, in this case, which is SQL. And then the third application is sort of like Grubhub or DoorDash or something like that, where it's a delivery service. And in this case, it's a microservices-based application. It doesn't use a single data service. It's using things like MongoDB, it's using a Kafka queue, and it's using MySQL as a transactional database to store our orders. So as a platform engineer, I need to manage these 3 applications for this fictional barbecue company. You as platform engineers are probably managing many, many more applications than just these 3. But we should be able to see some of the complexities and the issues just with these 3 applications. So let's look a little closer. Let's assume I have a need to deploy my application across 2 different cloud environments. In this case, we're just going to pick AWS and we're going to pick Azure just off the top of our heads. I've got an EKS cluster for Amazon. I've got an AKS cluster for Azure. I can deploy my front-end web service called Portworx Barbecue, and that runs as a container. But of course, we know we need some sort of a backing service for our 12-factor app. And in this case, we're just going to take the easy way out that's referred to by Humanitech in the reference architectures by using a managed database. So on the AWS side, we've got AWS Document DB, which is a MongoDB flavor. And on the Azure side, we're using Azure Cosmos DB, which again can give us the MongoDB flavor. Now, this seems very simple. As a platform engineer, we probably are like, well, this is no big deal. I'm managing two different environments here. They're both Kubernetes clusters, but they're slightly different. One thing I'm going to have to manage, a little bit of complexity. But then also I'm using a managed database, and those are different in those two clouds, a little bit additional complexity. But if I think through this a little further, I'm not just swiping my credit card and saying, yeah, I want this database, and I'm done with it. I don't have to think about it anymore. As platform engineers, we know that there's some additional things that come involved with this that we also have to manage, even if we didn't intend to. For example, in AWS, we're going to have to manage identity and access management policies. In Azure, we're going to have to manage some things in Azure AD, right? I need users and roles and things created. The two environments do this in two separate ways for these two services, so I still have to manage identity and access management somehow. I'm also going to have to manage VPCs in the AWS environment. My EKS cluster needs to be able to access that managed database, so I'm going to have to do some work there for networking. I've got my virtual private cloud in AWS. I'm going to have VNets in Azure. They're similar concepts, but again, different. If I keep going down this road, AWS is going to have security groups I have to manage. Azure has network security groups. In AWS, I'm going to have to take backups of my application. It's a managed database, but I still have to be able to back it up and restore it. So I'm using AWS backup for that in AWS and Azure backups in Azure. Completely different APIs. I need to code this twice for my internal development platform. And if I look at DR as an example, I might be using snapshot replication across regions or something like that with AWS. But in Azure, I can actually use a global distribution, right? So my Cosmos DB can be stretched across regions. Maybe I don't have any snapshot replication. Maybe it's a continuously updated database that's synced across regions. The point of this is this simple managed database that we thought was the easy option has all of these other dependencies that we still have to manage as platform engineers. On top of that, my platform admin or my platform engineer can probably manage everything in the Kubernetes clusters in both environments by themselves. But the clouds, if we have to interact with the clouds, then we're probably going to have to talk to at least one, if not two different cloud administrators, one for each cloud. And again, now we're talking about all these communication channels that are going to have to increase just so that we can manage the deployments of these applications, let alone talking to our application developers who are trying to use these platforms to deploy their app. Okay, so this was a pretty simple example with Portworx Barbecue, which is our easiest app to deploy. What happens when we get to a more complex application? So in this case, we're deploying Portworx Delivery. Portworx Delivery is a microservices-based application, and it requires multiple data services. I need AWS Document DB if I'm using managed databases again. I need some sort of a queuing service, so I could use AWS SQS for my queuing service in Amazon. And I can use AWS RDS for transactional to hold my orders for my MySQL database. If I flip over to Azure, I can do the same thing. I can use Azure Cosmos DB, Azure Database for MySQL, and Azure Message Bus. There's a service for each one of the parts of my application. That's not a problem. I can choose those and use those. But if we look back at the previous slide and see all of the dependencies we had to add just to manage some of those managed databases, you can see that a microservices-based application like this is going to be even more complex to manage for a platform engineering team. My pitch to you today is, what if we ran all of this in Kubernetes? If I'm doing everything in Kubernetes, including manage my stateful databases that need to persist, I can deploy my PX delivery application along with a MongoDB database, a MySQL database, and a Kafka queue, all in Kubernetes. If I want to do the same thing in Azure, it's the exact same deployment. So now as a platform engineer, I need to be able to build this one time, and now it's portable to any environment where I've got Kubernetes listed. Now, this probably sounds a little bit too good to be true, kind of simple. To a certain extent, I'm taking some liberties here. But in general, this plan works. The idea of this, keeping everything standardized across my environments, can help us limit the complexity and increase our velocity. Now, there's another option here. What if I'm looking at virtual machines versus containers? We've seen a lot of work recently, especially with what's going on with the Broadcom acquisition of VMware, where people are looking for alternatives. And what I've seen in the past is there's typically this vSphere layer or this vSphere stack that people have to manage, right? There's also a Kubernetes stack. Most new applications, especially platform engineering teams, you know this, most new applications are probably being deployed as containers. So I need some sort of a Kubernetes layer as well, even if they're for stateless applications. And each of these stacks, again, is going to increase our complexity because we have to have options. What do I do for performance monitoring? In vSphere, I'm probably using VCF operations or IBM Turbonomic or something like that to monitor it. In Kubernetes, I'm probably using Prometheus and Grafana. If I look at logging and auditing, I'm looking at like Log Insight or Datadog for the vSphere layer. But in Kubernetes, I'm probably using Elk, some sort of an Elk stack. For automation, I might be using VCF automation or vRealize automation. I might be using Argo CD or some sort of GitOps solution, maybe Flux. For backups, I'm using something like Veeam, or in Kubernetes, hopefully we're using Portworx, right? And then, of course, the last layer here for disaster recovery, we might be using Site Recovery Manager or Live Recovery from VMware. But in the Kubernetes layer, we need a different solution. Maybe you're using Portworx or something like that. The point is, I'm running these two stacks. I have to continue to manage these two stacks. Maybe I can get away with running both of those in a single stack. So again, now that we have things like KubeVirt, which is a project that allows us to run virtual machines and containers together in the same Kubernetes cluster, I can simplify my stack and only manage one set of software. One monitoring stack, one logging stack, an automation stack, backup and DR. I'm limiting the operations to one set of software. I'm reducing the amount of time that I have to spend procuring this software or getting licenses renewed every year. I'm increasing velocity by reducing the amount of work we're doing. Okay, Humanitech, meet me back at camera 2, would you? Okay, so earlier on, I might have been out of line. Maybe I shouldn't have come down on you so hard initially. This slide is a little bit self-serving to our point as well, so I'm going to let you off the hook. Can we call truce on this? So if we want to run everything in Kubernetes, we're going to need to have some sort of way to manage state. So typically, most people that were using Kubernetes clusters originally were putting stateless applications in those clusters. Typical web applications where you could delete them and redeploy them, and everything looked exactly the same. That's easy. Once we start managing state in Kubernetes, we have to take some additional precautions. So there's some things that you're going to need to do in Kubernetes to manage stateful databases instead of those managed services that you might choose from the cloud. You need to use high availability. You need to have things like volume placement services so I can put my databases maybe close to my applications. Sometimes that's necessary. We have to have a way to manage capacity. We need to be able to take care of migrations when we want to move our applications from one cluster to another, which kind of leads us into disaster recovery. We need to have a way to make sure that if something happens to our data center or wherever our Kubernetes cluster is running, that we can fail over to another data center where we've still got resources available. So you might be doing things like asynchronous disaster recovery, where we do things where we replicate on a schedule, or synchronous disaster recovery that has a 0 RPO option. We're going to need to take backups or snapshots or cloud snapshots or something so we can back up our data. We're going to have to do some things with AutoFS trim so we can reduce the amount of, when we delete data, we can clean that up and get our storage back. We need access to fast disks. We might need to prevent noisy neighbor issues, right? If I'm running lots of applications on the single Kubernetes cluster, often we set limits on CPU and memory, but we don't typically do things at the storage layer. We might need to have a solution that can do that as well. We're going to have encryption on our applications. And then what do we do when we accidentally delete something? Here's the self-serving part of this. These are capabilities that my company, Portworx Enterprise or Portworx by Pure Storage, can provide for you. The The 3 highlighted in orange here, you're going to actually see in our labs, which we're about to get to in just a second. So I apologize. This is a little self-serving, but I wanted to get you to the point here that there might be a better option for you to increase your velocity for your applications by using Kubernetes as that platform. So in the labs today, you're going to go through 4 different main labs, and then the 5th lab's kind of a sandbox where you can play around and do some additional things on your own if you want to. The first lab, we're going to show you how to provide persistent storage to pods. This is a very basic lab. We're going to be explaining persistent volumes and persistent volume claims to you and storage classes and things like that. You're going to deploy a very simple Nginx container and store some custom HTML in a persistent volume. And then we're going to delete the container and restart the container and show you, hey, look, all of my application data is still there in that persistent volume. So when the new container came up, my application still worked. Lab 2, you're going to deploy Portworx barbecue production application. So you're going to get to deploy Frank, our pig mascot for Portworx barbecue. You'll deploy our application with a MongoDB database, and then you're going to test high availability. So what happens if the node where our database is running fails? What happens to our application data and our application? Lab 3, we're going to test out capacity management. So you can do things like expand your persistent volumes. And then we're going to show you an automated way that you could also do this in some situations, depending on what your storage vendor is. And then lab 4, we're going to take a snapshot and take a group snapshot. You know, group snapshots might be something that we don't think about often, but what happens when I have a microservices-based application that's got multiple data services, and I need to snapshot or back those applications up at the same time to maintain application consistency? If I'm running managed databases in the cloud, how do I snapshot 2 different managed databases at the same moment so that if I restore them, my application's still consistent? And then again, lab 5 is an opportunity for you to play around in our lab, do anything you want there, kind of poke around. You can mess with the applications. There's some fun Easter eggs in the applications if you want to poke around in those, and just have some fun. When you get to your lab, I'm going to give you a link here in just a second. Let me post this in the chat so hopefully everyone can see it. There's a link to your application or to your labs. When you get into the lab, you're going to see a screen that looks something similar to what I have on my screen. On the right-hand side here that's highlighted, you can see your set of instructions. This will walk you through everything you need to do in the lab. It's going to give you some context about what's happening. It's going to explain the commands you're running, and you should just need to follow along with this and run the commands. You'll see some buttons here in the instructions, or you might see tabs across the top left-hand side of your labs. We have a terminal. We have some web applications that you're going to deploy, the ones we kind of talked about earlier. And sometimes it's going to ask you to switch to one of those tabs to perform some actions. Or you can also click on these buttons that are in the instructions. It'll flip the tab for you. When you need to run commands, these are live labs. You can type any command in this lab you want to. You can destroy the Kubernetes clusters that you're running on. Please be careful what commands you're running if you don't know what you're doing. But these are labs we're going to throw away at the end of the day. If you really mess something up, it's not a big deal. We can get you another lab if needed. In the bottom right-hand corner, you'll see a set of commands that you're going to run. So often you're going to be running these commands in the terminal. And there's a copy button where you can either copy the command and paste it into the terminal to run it, or you can just simply click this run button that's next to the commands, and it'll do the copy, paste, and run all for you all in one step. So it's pretty simple. Hopefully these labs are pretty fun and give you an idea of how you can manage storage in Kubernetes. And at this point, hopefully everybody can get logged in to the link that's posted in chat. We often recommend using an incognito window in your browser. It has solved some cookie issues that we've run into in the past. But you should be able to click these links and start your lab. And I'm going to hang out here. So I thank you for listening to my presentation.